GCE Advanced Level Chemistry Practical Series, Experiment number 30. Experimental determination of effect of acid concentration on the reaction rate between magnesium and acid reaction. The aim of this experiment is to investigate the effect of concentration of reactants on the rate of reaction, and apart from that, we are also aiming to determine the order of the reaction between magnesium and HCl by measuring the volume of hydrogen gas that is evolved. So we have now identified the aim of this experiment. Let's move on to identifying the reagents and the equipment we will be using for this experiment. Let's take a look at the chemicals and the equipment we will be using for this experiment. We will be using hydrochloric acid. So we have the hydrochloric stock bottle here. On the stock bottle, you would normally notice its molecular weight, its assay, and its density. So we can use these values to form HCl solution with a very specific concentration. And when we are trying to produce HCl solutions with different concentrations, we can use volumetric flasks. In this experiment, we need to produce a few solutions of HCl with different concentrations ranging from 1 moles per decimeters cube concentration all the way up to 0.2 moles per decimeters cube concentration. So we will be using these volumetric flasks to produce those solutions. Apart from that, we will be using measuring cylinders, beakers, a stopwatch, a stirring rod, magnesium strips. As you can see, students, the magnesium strips that we have here are coated with, or it has a gray color outer coating. So before we use the magnesium strip, we have to strip off this oxide layer or the coating that you have on the magnesium strip. So after stripping it off with sandpaper, it's going to appear like this. A shiny magnesium strip should be used for this experiment. So in your lab, you will observe your magnesium strips to be dull in color, just like this, because of the outer coating that it has. And you have to make sure when you are using magnesium for this experiment or any other experiment, you have to strip off the outer coating with the use of a sandpaper and obtain your magnesium like this. Right? You have to make sure the magnesium strip that you are using is not dull in its color. Apart from that, we will be using the setup that we have over here. We have a retort stand and we have clamped a boiling tube connected to a rubber stopper, and on top of the rubber stopper you can see a glass tube as well. And if you observe this boiling tube, from the bottom of the boiling tube 3 centimeters above, we have drawn a line, a black color line. So you would need this type of boiling tube where you have drawn a line 3 centimeters above the bottom of the boiling tube. So you would need a boiling tube where a line like this is drawn so that you can collect a constant amount of hydrogen gas when you are conducting this experiment. These are the equipment and the chemicals that you will be needing for this experiment. In the first part of our experiment, we are going to be preparing HCl solutions with different concentrations. So let's move on to the first part of our experiment, where we will measure a specific volume of HCl from our stock bottle, and we will proceed to prepare HCl solutions with different concentrations ranging from 1 moles per decimeters cube concentration all the way down to 0.2 moles per decimeters cube concentration. Let's move on to that part now. Students, in this part, we are going to be using a hydrochloric acid reagent bottle, and we are going to prepare first 1 moles per decimeters cube concentrated hydrochloric acid solution. After going through the information found on the reagent bottle that we have here, we have calculated to make 250 cubic centimeters of 1 moles per decimeters cube concentrated hydrochloric acid solution. We need to measure exactly 21.5 cubic centimeters of this hydrochloric acid that we have in front of us. So we are going to be using a measuring cylinder to measure 21.5 cubic centimeters of HCl. After that, we will be transferring that amount of HCl into a volumetric flask, and then we are going to add water all the way up to this calibration mark and mix it really well and finish preparing our 1 moles per decimeters cube concentrated hydrochloric acid solution. So now let's measure 21.5 cubic centimeters of HCl. Students, as you know, hydrochloric acid is an extremely strong acid, and it is going to be very corrosive if it comes into contact with your skin. So we have already measured 21.5 cubic centimeters of hydrochloric acid, as you can see over here. And even in the lab, when you are handling hydrochloric acid, please be careful around hydrochloric acid, especially at high concentrations. It could be quite dangerous to handle. So now, after we have measured exactly 21.5 cubic centimeters of our hydrochloric acid, we can keep the acid reagent bottle aside, and we can bring in our 250 cubic centimeter volumetric flask. And please note that there is a calibration mark over here. And so now, students, before we add the acid to our volumetric flask, we will be adding a little bit of water into our volumetric flask, because when you are adding water to the acid, it could be quite exothermic. But if you have a larger volume of water already present in the volumetric flask, and if you are adding acid to water, this released heat when acid is dissolving in water will be absorbed by a larger volume of water. So therefore, you will not necessarily see a huge increase in temperature. So to avoid any splash hazards or to avoid cracking of any glassware, we are going to first introduce a small amount of water, distilled water, into our volumetric flask. And then we are going to slowly add our HCl little by little, gradually, into this volumetric flask that already contains a small amount of water. After adding a little bit of HCl, you can proceed to swirl it around and dissolve the HCl. And then we can proceed to add a bit more HCl. And now we'll transfer the whole amount of HCl into our volumetric flask here. And we'll swirl it around. This slightly exothermic. And to make sure that we have transferred all of the acid into our volumetric flask, with the help of a wash bottle, we can wash our measuring cylinder also a couple of times, and we can add it to our volumetric flask like so. Right. After we have transferred all of the HCl into our volumetric flask, we can proceed to add water up to our calibration mark. We can use a wash bottle for this purpose. We can slowly add a little bit of water and you can mix the solution really well like this. And then you can proceed to add water all the way up to the calibration mark. After you come quite close to the calibration mark, please be careful when adding water with the help of a wash bottle. Instead, you can use a dropper and a little bit of distilled water, and you can bring your eye level to the calibration mark, or you can lift this volumetric flask all the way up to your eye level so that calibration mark is at your eye level. While holding it like this, you can proceed to add water with the help of a dropper. As soon as the bottom of the meniscus aligns with the calibration mark, you have to stop adding water, and we can see over here the bottom of the meniscus aligns perfectly with our calibration mark. You can place it on the table as well and observe that the bottom of the meniscus aligns perfectly with the calibration mark, indicating that we have now added the correct volume of water to this solution. So after adding water up to the correct mark, you can place the stopper and start mixing the solution. Now students, we have added exactly the right amount of water, and as you can see over here, so the bottom of the meniscus, the bottommost part of the meniscus is aligning really well with the calibration mark. Bottom of the meniscus should align with the calibration mark when you're producing a solution like this. So when you're adding water, you have to be very careful not to add too much water, because if you add even a few drops more, bottom of the meniscus will not align with the calibration mark. So at that point, you might have added too much water and you will have to start over. So after adding this amount of water, we have placed the stopper here. After placing the stopper, we can turn this volumetric flask upside down a couple of times to mix the solution really well. We can turn it upside down a few times so that we mix the solution really well and produce a homogeneous solution of HCl, and the concentration of this HCl is going to be 1 moles per decimeters cube. Now let's move on to making HCl solutions of different concentrations. Now students, we just observed how 1 moles per decimeters cube concentrated HCl solution was formed. It is now time for us to prepare 0.8, 0.6, 0.4 and 0.2 moles per decimeters cube concentrated HCl solutions. So to form these HCl solutions, or to prepare these HCl solutions, we will be using the 1 moles per decimeters cube HCl solution we prepared earlier. We have 1 moles per decimeters cube HCl solution we prepared earlier, and we have a beaker labeled 1 moles per decimeters cube HCl. So we are going to be adding the HCl solution we prepared into this beaker so that it will be easier for us to measure different volumes that we need for this part of our experiment. So in this beaker we have our 1 moles per decimeters cube concentrated HCl solution, and using a measuring cylinder we are going to measure 80 milliliters of this HCl solution and transfer it into a 100 ml volumetric flask. So we are going to measure 80 milliliters of 1 moles per decimeters cube HCl solution and transfer it into a 100 milliliter volumetric flask, and then we are going to add water all the way up to the calibration mark. So when you add water and prepare this new HCl solution, the concentration of this new HCl solution is going to be 0.8 moles per decimeters cube. So to produce that 0.8 moles per decimeters cube concentration solution, what did we do? We measure 80 milliliters or 80 cubic centimeters of 1 moles per decimeters cube HCl and transfer it to this volumetric flask, and then we fill it all the way up to the calibration mark. So let's go ahead and do that. We have our measuring cylinder here. We can start adding HCl. To make sure that you take the right amount of HCl, you can lift it up to your eye level. Now we have measured exactly 80 milliliters of HCl or 80 cubic centimeters of HCl using this measuring cylinder. Let's add this 80 milliliters of HCl into our volumetric flask. Keep in mind students, when you're transferring this volume into the volumetric flask, you should not be spilling any of the HCl. So you have to be very careful when you're transferring this volume to our volumetric flask. After that, we can take a little bit of distilled water and add to our measuring cylinder, and we can wash the interior walls of the measuring cylinder with this distilled water and transfer it into our volumetric flask as well. Now students, we have transferred all of the HCl that was present in our measuring cylinder into the volumetric flask. Then we can move on to adding more water to this volumetric flask with the use of a dropper. Since we have already reached the narrow part of our volumetric flask, it is wise to use a dropper at this point. If you make a mistake now, you will have to start preparing this solution all over again. So you will now bring it all the way up to your eye level and slowly add the last few drops of water until the meniscus perfectly aligns with the calibration line that you see over here. Now observe how the bottom of the meniscus aligns perfectly with our calibration mark. Then we can place the stopper. After placing the stopper, turn this volumetric flask upside down a few times to make a homogeneous solution of HCl. And then students, we have prepared a 0.8 moles per decimeters cube concentrated HCl solution. So let's transfer this HCl solution into the beaker that is labeled 0.8 moles per decimeters cube HCl. Now we are done preparing our 0.8 moles per decimeters cube concentrated HCl. We can move on to preparing our 0.6 moles per decimeters cube concentrated HCl. In order to do that, we'll have to measure 60 milliliters of 1 moles per decimeters cube concentrated HCl and transfer it into a volumetric flask. So let's take our HCl solution over here, 1 moles per decimeters cube HCl solution. And then measure exactly 60 milliliters of 1 moles per decimeters cube concentrated HCl. We have measured 60 milliliters of exactly 1 moles per decimeters cube concentrated HCl. Now we can proceed to transfer it into a volumetric flask. After transferring this 60 ml of 1 moles per decimeters cube concentrated HCl, we can wash our measuring cylinder and transfer that water also into the volumetric flask. And after that, since we still haven't reached the narrow end of the volumetric flask, we can proceed to add some water with the use of this distilled water that we have over here in a beaker. After we reach the narrow neck area of this volumetric flask, we will proceed to add our distilled water with the help of a dropper. Now everyone, we have produced another solution of HCl which has exactly 0.6 moles per decimeter cube concentration of HCl. We can see the calibrated mark and the meniscus aligns perfectly with the calibrated mark. Since you have seen it in the two previous instances, also you can imagine that in this instance also it is perfectly aligning. So whenever you are making any solution, it is very important to make sure that the bottom of the meniscus aligns perfectly with the calibration mark. If you accidentally add a little bit more water, you will have to restart the preparing of this solution. After adding the right amount of water, we can always turn it upside down to make a more homogeneous solution. Afterwards, students, we can now transfer a small portion of this solution into this beaker that is labeled 0.6 moles per decimeters cube. Now we have prepared two solutions, 0.8 and 0.6 moles per decimeters cube concentrated HCl solutions with the use of 0.1, with the use of 1.0 moles per decimeters cube HCl. Now we are going to be preparing 0.4 moles per decimeters cube concentrated HCl. Again, in order to do that, we would need more 1.0 moles per decimeters cube concentrated HCl. So we have taken small amount of that into this beaker. Now, in order to produce 0.4 moles per decimeter cube concentrated HCl, we are going to be taking another volumetric flask and we are going to transfer 40 cubic centimeters of HCl into this volumetric flask and then fill it all the way up to the calibrated mark. We can take a measuring cylinder here and we have a 1 moles per decimeters cube concentrated HCl. Let's measure 40 milliliters of this solution. Now we have measured exactly 40 milliliters of this solution. We can transfer it to this volumetric flask that we have over here. Like we did in the previous instances, we can wash our measuring cylinder with some distilled water. and then transfer that amount of distilled water into our volumetric flask as well. Afterwards, we can add distilled water with the use of a beaker to this volumetric flask. As always, the final few drops of the distilled water will be added with the help of a dropper. You can see when you're trying to make sure that you don't add too much water, you have to bring it to your eye level and use a dropper to add the right amount of water. Now you can see the bottom of the meniscus aligns perfectly with the calibrated mark. After that, you can place the stopper. You can turn the volumetric flask upside down a few times like this. Then you have prepared your 0.4 moles per decimeters cube concentrated HCl solution. So we can take this beaker that has the label 0.4 moles per decimeters cube HCl, and we will transfer a small amount of our 0.4 moles per decimeters cube concentrated HCl solution into our beaker. We can keep this volumetric flask aside, and now we can move on to preparing our 0.2 moles per decimeters cube concentrated HCl solution. So for that, we will need another volumetric flask. We can actually take 0.4 moles per decimeters cube concentrated HCl solution for this purpose as well, because when it comes to 0.2 moles per decimeters cube concentrated HCl, it has exactly half the concentration of this solution. So if you wish to dilute 0.4 moles per decimeters cube concentrated HCl twice and obtain 0.2 moles per decimeters cube HCl, you can do so. But to keep the consistency of what we were doing so far, we will be taking 20 milliliters of our 1.0 moles per decimeters cube concentrated HCl into a measuring cylinder, and then we are going to transfer that into a volumetric flask here and fill distilled water all the way up to the calibration mark. So let's measure 20 milliliters of 1 moles per decimeters cube concentrated HCl. We have measured exactly 20 milliliters of 1 moles per decimeters cube concentrated HCl. We can transfer that into this volumetric flask. After using the measuring cylinder, as we did in the previous experiments, we have now taken a small amount of water. We are going to wash this measuring cylinder, and we are going to introduce the water that is in the measuring cylinder now to our volumetric flask. After taking all of the HCl that was in the measuring cylinder inside our volumetric flask, we can proceed to add more water with the help of a beaker. And the final In this particular volumetric flask, the calibration mark is over here. So we can now use a dropper and add a few drops of water until the meniscus aligns well with the calibration mark. Now the bottom of the meniscus aligns perfectly with the calibration mark, meaning we have added the correct amount of water. We can now proceed to place the stopper on the volumetric flask and then turn it upside down a few times to mix the solution really well. Now students, we have prepared our final solution, which is 0.2 moles per decimeters cube concentrated HCl solution. Now we have prepared all 5 different HCl solutions that we need for this experiment, and finally find out the order of the reaction with the use of the data we collect throughout this experiment. Let's move on to the next part. Now students, in this part of our experiment, we are going to observe the reaction between magnesium and hydrochloric acid. Magnesium is a metal found on group 2 of our periodic table, and it is a reactive element. So therefore, when you react magnesium with HCl, you are going to observe the formation of magnesium chloride and hydrogen gas. So only observation you are going to note is the evolution of a colorless gas. And in this reaction, we are going to collect this colorless gas, and to make sure that we keep everything in this particular experiment series a constant, other than changing the concentration, we want to keep everything else a constant. So therefore, we are going to take similarly sized magnesium pieces for this experiment. We are going to measure about 4 centimeters of a magnesium strip that is already cleaned, and we can cut it using a scissor. And after that, we are going to make sure that we produce 5 other magnesium strips with the same length. We do this so that the magnesium surface that is exposed to the hydrochloric acid remains a constant. As you know, surface area affects the rate of the reaction. So if you have a magnesium strip that is longer, much longer than the others, then it would have a larger surface area, which would increase the rate of the reaction. So to eliminate this factor playing a role in this reaction, we make sure that we cut magnesium pieces that have, or we use magnesium pieces that have the same surface area. To ensure that they have the same surface area, we are going to measure magnesium pieces and their length. So if you get few magnesium pieces with the same length, make sure that the surface area that is exposed to the acid is going to remain a constant. When you keep the length of the magnesium strips a constant, the surface area exposed to the acid is going to be remaining a constant. So therefore, when you take a few magnesium strips that has the same length, we can be sure that the surface area is not going to increase or decrease the rate of the reaction. Because when you are conducting this experiment, we want to make sure only the change in concentration of HCl will affect the rate of the reaction. So we try our best to keep other factors such as temperature, such as the volume of hydrogen gas that is collected, and the surface area of the magnesium strip that is exposed to the HCl a constant. So now we have cut 5 pieces of magnesium with equal length. So we can now move on to adding these magnesium strips to a rubber stopper and conducting this experiment. Students, now we are going to react magnesium with HCl, and we are going to observe how the rate of this reaction is going to change when the concentration of HCl is changed. To observe that, we have prepared a few solutions of HCl having different concentrations. The HCl concentration range from 0.2 moles per decimeters cube all the way up to 1.0 moles per decimeters cube. We are going to measure the rate of this reaction by collecting a constant volume of hydrogen gas. We are going to observe when magnesium is reacted with these different HCl solutions, how long it actually takes for each of these reactions to produce a constant volume of hydrogen gas. To keep the volume of hydrogen gas collected a constant, we have made a mark here in this particular boiling tube. You can see from the bottom of the boiling tube, 3 centimeters high, we have drawn a mark. So when we are carrying out this experiment, we are first going to fill this boiling tube with HCl all the way to the top, and then we are going to place a magnesium strip on the rubber stopper like so, and after doing that, we will be inserting this rubber stopper along with the magnesium tube into this boiling tube with HCl now, and we are going to quickly turn it upside down. So as the HCl and magnesium come into contact with one another, there will be a reaction taking place, producing hydrogen gas. The hydrogen gas produced will be moving up and will be getting collected over here. And the water that is displaced from this area will be allowed to run through this rubber tubing, actually a glass tubing that we have here. So it will go through this glass tube and will get collected at the beaker that we have over here. And as soon as we have a constant volume that is marked by this black color line that we have over here, as soon as we have collected a constant volume of hydrogen gas, we will be measuring the time that it took to collect this amount of hydrogen gas. I may have forgotten to mention, as soon as we turn this tube upside down, we will be starting the stopwatch, and as soon as we have collected this specific volume of hydrogen gas, we will be stopping the stopwatch and will be observing how long it took for this hydrogen gas to get collected. So without further ado, now we can move on to the first reaction, where we will be taking 0.2 moles per decimeters cube concentrated HCl and introducing a piece of magnesium onto this HCl. And we'll be following the steps that I mentioned earlier. We have a strip of magnesium here. We have sanded it down and we have prepared it for this experiment, and we are going to place it on this rubber stopper. After placing it securely on the rubber stopper, we are going to fill this boiling tube with 0.2 moles per decimeters cube concentrated HCl. So we have prepared this 0.2 moles per decimeters cube concentrated HCl. We will fill this boiling tube all the way to the top with this 0.2 moles per decimeters cube concentrated HCl solution. Then students, as soon as you plug in the rubber stopper, we have to turn the tube upside down, and as soon as you do that, you have to turn on your stopwatch. So we will keep the stopwatch close by, so it will be easier for us to turn it on as soon as we turn it upside down. So when you are doing this experiment, you have to make sure that as soon as you introduce the magnesium piece into the HCl and turn upside down, that you turn on the stopwatch. Otherwise, you will not be able to measure the time that it took for the hydrogen gas to get collected all the way up to this mark accurately. Now, as you can see, students, the magnesium strip is reacting. The magnesium strip is reacting with the HCl, and you can observe magnesium strip coming into contact with HCl and producing hydrogen gas. And as the hydrogen gas gets collected over here, the water from that area will get displaced and will come out of this glass tube that we have connected to our rubber stopper. So we have turned on our stopwatch. We have to wait till hydrogen gas gets filled all the way to this mark that we have made on this boiling tube. And after that, we can move on to our next experiment. Now students, you can see there is a certain amount of hydrogen gas that is collected here, and it is still not collected all the way down to this black color mark that we have made on the boiling tube. The time that it has taken to fill this amount of hydrogen gas into the boiling tube is 3 minutes and 50 seconds. We have to wait a little bit longer until this entire area is filled with hydrogen gas. So we want to observe the water level at this black color mark that we have over here. As the water level gets down to this black color mark, we will stop the stopwatch and take note of the time it took for hydrogen gas to get collected all the way down to the mark that we have made on the boiling tube. Now, students, it has been 5 minutes. It is 5 minutes now. We are getting close to filling hydrogen all the way down to this black mark. So we'll stay prepared to stop the stopwatch. Students, now we have collected hydrogen gas up to this level, and the time it took for that reaction to take place is 5 minutes and 35 seconds. 5 minutes and 35 seconds. So we will make note of that time, and then we can move on to the next reaction, where we will be reacting the magnesium strip with an HCl solution that has a 0.4 moles per decimeters cube concentration. Now we move on to the second experiment. In this experiment as well, we will be taking a strip of magnesium that is equal in length to the length of the magnesium strip that was used in the previous step. All of these magnesium pieces that we have with us are now going to be equal in length, so that we keep the surface area that is exposed to HCl constant. We need to make sure the surface area that is exposed to the hydrochloric acid are constant. So we have measured each magnesium piece in such a way that each of them have a similar length. Now we have fixed this magnesium strip onto our rubber stopper. We will be taking our 0.4 moles per decimeters cube HCl. After taking this HCl solution, we can add 0.4 moles per decimeters cube concentrated HCl all the way to the top. Now students, this is very important. If you leave a small gap like this, if you can observe, if you leave a small gap like this, and then when you place the rubber stopper, there's going to be a small air gap between the stopper and the water level. So this would result in an already filled amount of gas in the boiling tube. So this will interfere in our readings when you are trying to measure the time that it takes to collect a certain amount of hydrogen gas. So please make sure that you add HCl all the way to the top. Now you can see HCl is filled all the way to the top. Then we have to be ready with our stopwatch. As soon as we introduce this magnesium strip, we will be turning this setup upside down, and we'll be starting the stopwatch as well. So let's do that now. So as you can see, as soon as you turn the boiling tube upside down, you will have to turn on the stopwatch. After turning on the stopwatch, you will have to wait till the hydrogen gas gets collected all the way down to the mark that we have made on our boiling tube. As you can see, compared to the previous reaction, this reaction is happening a little faster. Actually, the previous reaction used 0.2 moles per decimeters cube concentrated HCl. Now, this HCl solution is 0.2 moles per decimeters cube concentrated, meaning this HCl solution is twice as much concentrated compared to the previous solution. So you can observe the reaction rate is somewhat higher. We are coming close to collecting hydrogen gas all the way up to this line, so we will be ready with the stopwatch. Now we have stopped the stopwatch, and the time reading is 1 minute and 26 seconds. 1 minute and 26 seconds. So the time that it took for hydrogen gas to get collected all the way up to this black line that we have made on the boiling tube is 1 minute and 26 seconds. Now students, we will be removing this setup. In the third experiment, we are going to react the magnesium strip with 0.6 moles per decimeters cube concentrated HCl. Let's move on to that experiment. Now students, let's move on to reacting the magnesium strip with 0.6 moles per decimeters cube concentrated HCl. We'll take another magnesium strip that we have prepared earlier. We will secure it on this rubber stopper like so, and then let's fill the boiling tube that we have with us all the way up to the top. Keep in mind students, you should be filling it all the way to the top. And after filling it all the way to the top, you can place this rubber stopper, turn it upside down, and start your stopwatch. So we are going to be placing this magnesium strip here. As soon as we do that, we'll turn it upside down and turn on our stopwatch. As you can see students, the reaction is happening much faster, and within 27 seconds, we have collected the hydrogen gas all the way to the mark that we have made here. So it took exactly 27 seconds. So now we know how fast the reaction will proceed when we increase the concentration of HCl. Earlier on, the very first reaction we did with 0.2 mHCl, it took over 5 minutes. And the next time around when we used 0.4 moles per decimeters cube concentrated HCl, it took a little over 1 minute and 30 seconds. And now we have 27 seconds taken for the magnesium strip to react with HCl to produce hydrogen gas all the way up to this mark that we have made on the boiling tube. So we can now have an idea that this reaction is happening faster when we increase the concentration of HCl. Higher the concentration, faster the rate. So let's note down these times and move on to our fourth experiment, where we'll be reacting magnesium with 0.8 moles per decimeters cube concentrated HCl. Now we are going to react another magnesium metal piece with 0.8 moles per decimeters cube concentrated HCl solution. We'll be following the same steps. We'll take the rubber stopper, place the magnesium strip on the rubber stopper securely, as you can see. After placing it securely, we are going to be filling our boiling tube with 0.8 moles per decimeters cube concentrated HCl all the way to the top. After filling the boiling tube all the way to the top with our HCl solution, we can take our rubber stopper along with the magnesium strip and we can place it and start our stopwatch after turning the boiling tube upside down. So let's get ready to do that. We will be placing this rubber stopper and starting the stopwatch soon after we turn it upside down. Students, it took 13 seconds. It took 13 seconds for this reaction to take place. Now we saw how fast the reaction is proceeding every time we increase the HCl concentration. So we can very clearly observe that HCl concentration affects the rate of the reaction. Now let's move on to the final reaction, where we are going to be reacting the magnesium strip with HCl solution that has 1 moles per decimeters cube concentration. So we have a 1.0 mole per decimeters cube concentrated HCl solution here, and we are going to now react the magnesium strip with this solution and observe how fast the reaction is taking place. Now students, we can take our final strip of magnesium that we have with us here, and we will be placing it again on our rubber stopper. We will place it securely, and then we will be filling our boiling tube all the way to the top. After doing so, we will be inserting this rubber stopper and starting the stopwatch as soon as we turn the boiling tube upside down. If you are conducting this experiment in the lab and you have a lab assistant, you can get your lab assistant to do this, as it will be difficult for one person to place the rubber stopper and start the stopwatch at the same time. However, if you are doing it on your own, as soon as you place the rubber stopper, turn it upside down and quickly start your stopwatch. So we are going to be doing the same few steps that we have done in the previous experiments. And we have collected hydrogen gas all the way up to the mark that we have made. Now let's observe the time that it took for hydrogen gas to get collected all the way up to the black line that we have over here. It has taken 5.9 seconds. 5.9 seconds. We can round it off to 6 seconds as well. So the stopwatch reads 5.9 seconds. Now students, to collect hydrogen gas all the way down to this black line that we have made here in the boiling tube, in our last experiment, it took us 5.9 seconds, or if you're rounding it off, it will be 6 seconds. Now we have observed how the reaction rate changes when we increase the concentration of the HCl that we have used. Just to give you a summary before we conclude this experiment, we wanted to make sure that we measure the rate of the reaction by measuring the volume of hydrogen gas that is collected here. So to make sure that we keep the volume of hydrogen gas that is collected a constant, we used a boiling tube and we drew a line 3 centimeters from the bottom of the boiling tube. So we measured how long it takes for each reaction to collect hydrogen gas all the way to this black color line that we have drawn on the boiling tube. And we observed, as we increase the HCl concentration, the time that it took for the hydrogen to get collected reduced. When we had 0.2 moles per decimeters cube concentrated HCl reacting with magnesium, we saw it took over 5 minutes and 30 seconds. And then when it was reacted with 0.4 moles per decimeters cube concentrated HCl, it took only 1 minute and 30 seconds. And then when it comes to our third experiment, when we reacted HCl that has a concentration of 0.6 moles per decimeters cube concentration, it took less than 30 seconds, around 27 seconds. When it comes to our 0.8 moles per decimeters cube concentrated HCl, it took around 13 seconds. And when it comes to 1.0 moles per decimeters cube concentrated HCl, we saw the same amount of hydrogen gas was collected within a very small time period, like 6 seconds or under 6 seconds. When it comes to 1.0 moles per decimeters cube concentrated HCl, we saw we were able to collect the same amount of hydrogen gas in under 6 seconds. So we can very clearly observe, as we increase the concentration of HCl while keeping other conditions a constant, such as the length of the magnesium strip, the temperature. We didn't increase the temperature or decrease the temperature of the system. When we keep other factors a constant and change only the concentration, we observe the rate of the reaction increases as we increase the concentration of our HCl solutions. Let's move on to our next session, where we'll be calculating the order of the reaction, as well as where we'll be looking at some questions and important theory parts revolving around this experiment. Experiment number 30, additional experiment, experimental determination of the order of the reaction between calcium carbonate and HCl. The aim of this experiment is to determine the order of the reaction between calcium carbonate and HCl by observing the mass loss as the reaction proceeds. So students, in this experiment, we are going to measure 100 grams of calcium carbonate into a beaker, and we are going to react it with 2 moles per decimeters cube concentrated HCl, 1.5 moles per decimeters cube concentrated HCl, and 1 moles per decimeters cube HCl. When it comes to each of these concentrations, we are going to take exactly 100 milliliters of each of these solutions. And when we mix these two reactants together, calcium carbonate and HCl together, the final reaction mixture will initially have an initial mass. And using a digital balance, we will measure that mass. After measuring the mass, students, when the reaction proceeds, in every 20-minute intervals, we are going to measure the mass of the reaction mixture. And you would observe, as the reaction proceeds, the mass of the reaction mixture decreases. Now, this is because calcium carbonate and HCl, when reacted, will produce carbon dioxide gas. Calcium carbonate, when reacted with HCl, will produce calcium chloride, carbon dioxide, and water. And carbon dioxide is a gas. So this gas will be removed from the system. As a gas escapes the system, you will see the mass of the system will decrease, or mass of the reaction mixture will decrease. So this decrease of mass can be used to measure the order of the reaction between calcium carbonate and HCl. So when you're using this mass loss method to calculate the order of the reaction of a given reaction, you have to make sure that the reaction you are talking about releases a gas with a significant mass. When it comes to carbon dioxide, it has a molar mass of 44 grams per mole. So it's somewhat of a large mass. If you try to conduct a similar experiment but with hydrogen gas emission and weight loss that is going to be resultant due to the emission of hydrogen gas, then it will not be very successful. This is because you will not be able to see a significant reduction in mass as the reaction proceeds, because hydrogen gas has a very small molar mass. Even if a single mole
of hydrogen gas is evolved from the reaction mixture, the mass difference is going to be only 2 grams, because the molar mass of hydrogen is 2 grams per mole. So the gas that is evolved should be having a significant mass, unless you will not be able to use this method to calculate the order of the reaction when it comes to a reaction like this. So students, that is one key information that you should keep in mind when it comes to using the mass loss method. The mass is lost in the reaction mixture because a gas is evolved. So if you're using this particular mass loss method to calculate the order of a reaction, you have to make sure that the gas that is evolved, that the gas that is escaping the system, has a significant mass. If you are using a system where hydrogen gas is evolved, you can't use a system like that and calculate its order using the mass loss method. It will be better to use a separate method or different method where you collect the amount of hydrogen gas that is produced, as we saw in the previous example. Right? So mass loss method is a better suited method to systems where heavier gases such as carbon dioxide is evolved. So when carbon dioxide is evolved, for example, if 1 mole of carbon dioxide is evolved, there's going to be a mass difference of 44 grams, which is a significant mass difference, which will be very clearly seen in a setup like this. So students, this is why when it comes to the mass loss method, we would use a reaction where a gas like carbon dioxide is released. So in this reaction also, we can see calcium carbonate with HCl, like I mentioned earlier, will produce carbon dioxide. So to carry out this experiment, these are the equipment we'll be using. We'll be using calcium carbonate, 2 moles per decimeter cube concentrated HCl, 1.5 moles per decimeter cube concentrated HCl, and 1 moles per decimeter cube concentrated HCl. And in each of these beakers, we have measured exactly 100 milliliters of these solutions. And these solutions were prepared using volumetric flasks, so their concentration is accurate. And their volumes were measured using measuring cylinders, so therefore their volumes are also accurate. So apart from this, we'll be using this equipment as well. Over here we have a digital balance. You can see a digital balance over here, and we'll be using a stopwatch as well to obtain the mass readings at 20-second intervals. We'll be using both of these devices. We'll be using the digital balance as well as the stopwatch to obtain the mass readings at specific time intervals. Now, without further ado, let's move on to actually conducting this experiment. Now students, we are going to first take a beaker, a clean empty beaker, and we will be weighing the mass of this beaker. Before doing so, let's turn on our digital balance. Make sure the unit is in grams, and then we'll place this beaker over here. The mass of the beaker is 79.06 grams. 79.06 grams, and we are going to be measuring 100 grams of calcium carbonate into this. To make it easier for us, we can use the tare function. So we will now take calcium carbonate. We have calcium carbonate here. You can see we are using calcium carbonate solid, and we will have to measure 100 grams of calcium carbonate into this beaker. Now we have measured exactly 100 grams of calcium carbonate. We can now use the tare function again because we need to measure the overall mass of both calcium carbonate and the beaker. So now let's place it over here. You can see the overall weight of this beaker plus the calcium carbonate in it is 179.06 as you can see over here. So we have now measured exactly 100 grams of calcium carbonate into this. We have to now add our 1 moles per decimeters cube concentrated HCl solution into this, and as soon as you add this 1 moles per decimeters cube concentrated solution, we will start our stopwatch, and at every 20-second interval we will be noting down the mass of this particular reaction mixture. The mass will be given over here in the digital balance. So the digital balance reading will be taken down every 20 seconds. Now we will place this again on the scale. Now students, we are going to add 1 moles per decimeters cube concentrated HCl to this. So you can see the mass reading is 179.06, and as we add the HCl, we will be turning on our stopwatch. And every 20 seconds we will be taking our mass reading over here. You can see carbon dioxide is evolved and the mass is changing. At 20, 279.13. At 40 seconds, 279.17, 07, not 17, 279.07. We are waiting till it is 60. 278.96. 278.85. 278.73. 278.63. 278.57. And 278.51. So students, now we have taken 8 readings. You wouldn't need all of these 8 readings, but in case you do need it, that's why we go up to 8 readings, but you can actually stop it when you have fewer readings than this. So You can see as the reaction proceeded, you can see carbon dioxide is produced, and even when we use this type of very large amounts of, or we have used 100 grams of calcium carbonate and 100 milliliters of 1 moles per decimeters cube concentrated HCl, still the mass differences you see are very small. It's not extremely large. Even when you use a reaction setting like that, you can see there is not going to be huge changes in mass when you have a concentration like 1 moles per decimeters cube concentrated HCl solution reacting with calcium carbonate. So this is why it is a must to have a heavier gas released when we are using this type of method to calculate the order of the reaction between our two reagents. So now we can set it aside and move on to the next step. Now students, we are going to be doing the same few steps for another solution of HCl. Now this HCl solution has a concentration of 1.5 moles per decimeters cube. So we will be measuring 100 grams of calcium carbonate using the same beaker we used earlier. Now we have it cleaned and dried. So we will be using the same beaker throughout. And when it comes to the reaction that we are going to be carrying out, the only difference between the first and the second reaction would be when it comes to the second reaction, the solution that we are using will have a different concentration. Mass of the calcium carbonate we use will be the same, and the mass of the beaker will be the same. There might be a slight difference in the mass of calcium carbonate because sometimes we can't measure exactly 100 grams of calcium carbonate. Apart from that, the steps that we follow will be the same. So first, let's place our beaker on the balance like so. The beaker has a mass of 79.06 grams. Now students, after measuring the mass of the beaker, we can proceed to adding calcium carbonate to this beaker. We are going to add 100 grams to this beaker. So when you add 100 grams to this beaker's original mass was 79.06. After adding 100 grams, it should read 179.06. So we will add 100 grams of calcium carbonate. Now the reading is at 177.46. So we need 179.06. So let's remove small amount of calcium carbonate. I just removed a small amount of calcium carbonate, and the final mass we have obtained is 179.09, indicating the mass of calcium carbonate we have measured is 100.03. So that is a good measurement of calcium carbonate. So we have measured 100.03 grams of calcium carbonate. Now we can proceed to adding HCl onto this reaction mixture, and we will note down the changes in mass every 20 seconds. So as we add this, we will start our stopwatch as well. We have 1.5 moles per decimeter cube concentrated HCl. You can see the concentration of HCl. So now we will add our HCl and we will start the stopwatch as well. And we will note down the mass reading here every 20 seconds. The first reading is going to be 180.2 180.23 grams. 180.23 grams. The second reading is going to be 280.0 grams. Third reading is going to be 279.9 or 87 grams, 279.87 grams. That is the third reading. Fourth reading is going to be 279.74 grams. 279.74 grams is our fourth reading. Our fifth reading is going to be 279.62 grams. 279.62 grams. Our sixth reading is coming up next, and that will be 279.46 grams. 279.46 grams. And then we have our seventh reading. It's going to be 279.36 grams. Then we move on to our eighth reading. Eighth reading is 279.23 grams. When it comes to our ninth reading is 279.13 grams. Ninth reading is 279.13 grams. And the 10th and the last reading is going to be 279.08 grams. 279.08 grams. So students, this is our second experiment, or we are repeating it for the second time now. So as you can see, when you react HCl and calcium carbonate together, you can see they will react to produce carbon dioxide. Calcium carbonate, when react with HCl, will release carbon dioxide. You can see carbon dioxide gas is emitted. You can see the bubbling of this reaction mixture, and as it bubbles, you can see how the mass of the entire reaction mixture reduces. So students, this is our second part of this additional experiment. We observed how the mass readings are changing, and now it is time for us to move on to our third and the final part of this experiment. So let's move on to the third and the final part of our experiment, where we'll be using 2 moles per decimeter cube concentrated HCl solution. Now students, we are going to repeat the same reaction but with a different concentration of HCl solution. So we will be using an HCl solution that has a concentration of 2.0 moles per decimeter cube. So as we did earlier, we will be measuring 100 grams of calcium carbonate. So we will be measuring 100 grams of calcium carbonate as we did before. You can see we started off with 79.06 grams. That is the mass of this particular beaker. We have been using the same beaker all 3 times to keep everything a constant. So the mass of this beaker remain the same. The mass of the beaker is 79.06. So if we want to take 100 grams of calcium carbonate, we will have to get a final reading of 179.06. We have measured a little bit over the required weight. So students, now we have measured 179.10 grams, indicating that we have measured exactly 100.04 grams of calcium carbonate. You can see the final weight is 179.10. The mass of the beaker was 79.06. So the amount of calcium carbonate in here is 100.04 grams. Now students, as I mentioned earlier, we have measured 100.04 grams. So the final reading is 179.10. The mass of the beaker is 79.06. The mass of the calcium carbonate we measured is the mass of calcium carbonate we measured is 100.04 grams, and when you add these two values together you get 179.10 grams. So students, after observing this mass, we can now take our 2 moles per decimeter cube concentrated HCl solution, and we can add this HCl solution while we turn on our stopwatch as we did before. And then we are going to measure or take the mass readings every 20 seconds. So the first reading is going to be 279.80, 279.80 was our first reading at 20 seconds. Second reading would be 279.50. Third reading is going to be 279.23. Is the third reading. Fourth reading is going to be 279.02. Fifth reading is going to be 278.78. 278.78. We are moving on to the sixth reading. Sixth reading is 278.61 or 60 actually. 278.60. That is the sixth reading. We will take 10 readings for this one as well. When it comes to the seventh reading, it is 278.44. 278.44. We're moving on to the eighth reading. Eighth reading is 278.27, 278.27, and after this we'll be moving on to the ninth reading. Ninth reading is 278.16, 278.16, and finally the 10th reading. We will move on to the 10th reading as well. 10th reading would be 278.01. So students, you can very clearly see as time passes by, the mass changes, and when it comes to a higher concentration of HCl, you have to, through the measurements you obtained, you have to calculate if the reaction was happening faster or more slowly. So that's why we take all of these readings. By observing these readings, by plotting all of these readings in a graph, you can calculate the order of this reaction. When we change the HCl concentration, we can see how the rate of the reaction changed, and by observing that, we can calculate the order of the reaction. So this is the additional experiment that comes under experiment number 30. And after observing these three reactions we conducted in the lab today, it is now time for us to move on out of the lab and move on to questions and additional theory parts that are revolving around this experiment. So students, let's move on to the next part.